The science of chemistry. As we begin this course, certainly want a definition that is useful and functional to you. This definition that I'm about to write out is somewhat wordy, but it is accurate in terms of how chemistry comes together. Chemistry is the study of the composition, structure, and properties of matter. Okay. And the changes in composition, structure, and properties that matter undergoes. Basically, the study of chemistry is the study of matter. And matter, by definition, three stripes is by definition, anything having weight and occupies space. Well, it's not hard to imagine that is everything that we can conceive of, seen or not seen. So in the context of studying chemistry or the study of matter, it is important that we understand how to break the idea of matter into categories and subclasses and down to something that's a little easier to study. Generally, matter is divided into two broad categories, generally mixtures and substances. Mixtures are physical combinations of two or more substances that have not chemically interacted. So this, in terms of mixtures, these are all physical combinations. Whereas when we talk about substances, we're talking about pure homogeneous systems that are chemical in nature, in their formation and in their separation or their existence. So substances are all chemical in nature. Just make it that. Now, of course, that embodies a significantly large quantity of materials, also matter, and so it's important that we break these down into even simpler forms. Mixtures are typically categorized as homogeneous and heterogeneous. So heterogeneous, and then homogeneous. The heterogeneous simply means not consistent properties throughout. If you took samples of a mixture, its percent composition would be variable. And it refers, of course, to percent composition. So if you took, again, if you took a sample, 2 or 3 samples, you would find that whatever the mixture consists of, you have sulfur, which is bright yellow powder, and gunpowder, black, mix them together, and then take samples and analyze for percent composition. You'd find there would be a broad variation in each one. However, homogeneous is consistent properties. Throughout, that is, the percent composition for all samples is constant, or does not vary. Like that. So, in studying chemistry, we're again breaking things down into a simpler context. Now, the study of mixtures and homogeneous and heterogeneous systems are distributed throughout the course. And one particular chapter that deals with the homogeneous mixture is that of solutions. This up a little bit. So one example of a homogeneous mixture are solutions. Solutions, by definition, is simply a homogeneous mixture. With consistent properties throughout. And these are easy to visualize in terms of what you have to consider is a spoon of sugar and dissolved in a glass or beaker of water. It becomes clear, and there are some properties of solutions that you will eventually learn about as we get deeper into the course. But that is a specific chapter that we will cover by itself. Anyway, that's as far as we're going to go with the definitions on the mixtures. The other side of this category collection is the idea of substances. And now all substances are homogeneous and consist of really 2 categories. So we'll bring that one down here. Quite simply, substances all are homogeneous in nature. Okay. And are divided into 2 broad classifications or categories. One are the elements, the other are compounds. Now, elements, of course, as you are familiar with, can be found listed systematically on the periodic table. Elements are made up of course, atoms. Atoms, when the terminology is used, atoms refer to an individual entity, whereas elements refer to a whole lot of that individual entity. And same way with compounds. Compounds are made up of molecules, and a molecule is an entity or single unit structure of the compound, and the compounds represent a whole lot of the individual structures. Well, at this point, we need to give you a fundamental definition of each one of these, and let's start with elements. And the same atoms. An atom is an individual unit, and elements is a lot of units, but they're still essentially the same definition. This is the smallest entity of a substance with unique physical and chemical properties. That cannot be broken down by ordinary chemical or physical means. Oops. I need to do something here. You'll probably read a little bit easier that way, huh? Okay. Now, when we talk about ordinary chemical and physical means, what we're referring to, make that look like a MEAN, that refers to heat, light, electricity. Now, we have in the course of studying chemistry, chemical reactions, which cause the molecular structures and atomic structures to undergo things like ionization, gaining, losing electrons, and so forth. But in terms of its basic character, sodium remains sodium regardless of the reaction it's going through. Or calcium, same way, or chlorine, or oxygen, or whatever you're studying, it remains oxygen because it is indivisible just by hitting it with heat, light, or electricity. So hence the first definition of the simplest elements or substances that we can consider are certainly the elements. Yes, the definitions are somewhat wordy, and it takes a minute to, of course, pen them out for you. But it is very important that you see the difference from a technical standpoint, that is the fundamental definitions of each. It's important that you understand how the elements remain elements, or the compounds remains compounds throughout the context of studying them. And so as we get deeper into the course, you'll understand more about the principles and rules that govern whether or not they don't break down, or govern whether or not they do break down into constituent components by chemical and physical process. I call it organization of chem study. And as just mentioned, is based upon very famous John Dalton developed a set of postulates that describe the behavior of matter from a fundamental standpoint. Now, just as a trivia note in here, the first atomic theory was actually proposed and penned in the literature 600 BC by Democritus, in which he proposed what we call a divisional unit, or the smallest particle of matter. And in that, he says, if you take a sample of matter and divide it in half, and then take 1/2 of that sample, divide it in half, and then half of that one, and divide it in half again, and continue to do that, you will reach what we call an indivisible particle. The indivisible particle is a Greek word called the atomos particle. Atomoius. I'm sorry. Atomos particle, that's good enough. And of course, that is the source of our word for atom. It's an indivisible particle, is what the essence of that definition refers to. And that was the first atomic theory. But that was exclusively upon a philosophical point of view. The Dalton atomic theory is based upon the scientific method, and all of his conclusions were based upon scientific observation and observations from experiment. Okay, now what's significant about Dalton's atomic theory is starts off with the most fundamental particle. In his treatise, it was the atom, but we know today that the atom in itself is broken down into even simpler, more fundamental particles, which we call fundamental particles. And so that's the way I want to outline this. So from Dalton's atomic theory, we will study chemistry in the following context. We will first look at fundamental particles, which you recognize for the most part: protons, neutrons, and of course electrons. And we will put those together into atoms, which are defined in terms of elements and organized per the periodic table. And then we will look at molecules and compounds, which is based upon a classification of compound types. There are two classifications. Well, actually, yeah, let's keep it that. Two classifications: ionic and molecular type compounds. Make that neater. So you see how we're getting it into a more digestible format, so that it's a little easier to study if you break it down into the more fundamental topics. Well, molecules and atoms interact, or compounds and elements interact, by process of chemical reaction. Bring that up here. And the changes in composition, structure, and property occur, and that's what the essence of our study is anyway. How do these changes take place, and what are the results of those changes? So we've taken atoms and molecules, we've looked at that, and then we'll interact them. Now, in this course, we have a specific classification of types of reactions, and at the appropriate time, we will present those and how they are important and interpreted in the study of matter. Now, let's see if I want anything else. Well, anyway, so chemical reactions essentially is the essence of this sequence. Now, chemical reactions only produces one of three things: a solid, a liquid, or a gas. Now, there are, of course, many forms of each one and in their existence. But in essence, as far as our interests go, they are simply going to produce a solid or a liquid or a gas. Now, in some cases, we will have solution phase process or reactions, and we will include aqueous phase reactions. No, I'm going to write. And those are designated, of course, as I just said, AQ, and typically put into parentheses AQ. We do not work with plasmas in this course. That's a temperatures above 5,000 degrees. So everything we do is going to be below 5,000 degrees. I know you're relieved to hear that. But at any rate, now, what can be generated out of solids, liquids, and gases, the states of matter, or solutions? So you can mix a solid into a liquid. It's an easiest one to understand. So we have the final category of our simplification of study, chem study, is these generate solutions. And there are multiple types of solutions, which are homogeneous mixtures of solids, liquids, and or gases. So if you dissolve a solid in a large quantity of water, sugar into water, of course it clears and assumes the solid will assume the state of existence of the solvent, and you'll learn about that later on. But that's the essence of our study of general chemistry, and it goes through this point, and that's relative to chapter right now through the chapter 12. And now I don't cover all of chapter 12. just some items in chapter 12 that you will need to the next level, like solution reactions, but they're pretty straightforward. Now, beyond that is Chem 2. Now, just for your edification, Chem 2 is simply the study of reactions. And yes, I want you to be aware of these terms and why they are as they are. Now, I'm not asking you to work problems and things on them, but this is what the study of reactions breaks down to, and is part of the organization of chemistry. The study of chemical reactions is broken into three big picture topics: chemical kinetics, chemical equilibrium, and chemical thermodynamics. Each one of these has a major purpose in its existence. Kinetics deals with rates of reaction. Now, that doesn't make it look like a R-A-T-E. Rate of reaction. Chemical equilibrium deals with extent of reaction. The best example I can give you with extent of reaction, if you have a beaker and a quantity of water, and the moment you pour the water in there, it begins to evaporate, sending particles into the vapor phase up here. If you close that off, it reaches a point at which there's no change in the depth of the water as you look at it. Well, that means that particles that are evaporating are also condensing at the same rate. And that's what we talk about, extent of reaction. Under what conditions will it reach an equilibrium? And so the extent of reaction is the point of equilibrium, is what the essence of this little notation is. But at the appropriate time in Chem 2, if you stay with me through that, I will certainly outline the principles that go behind this. And finally, chemical thermodynamics is the determining the feasibility. That's the whole essence of thermodynamics, is feasibility of reaction. And it's pretty much self-explanatory in that under the proper condition, under the conditions specified, let's put it that way, under the conditions specified, will the reaction proceed to products? That's feasibility. And using principles of thermodynamics, you can determine whether a reaction under these conditions will proceed to generate products in the context of running the reaction. And you can modify those conditions so that it does generate products or inhibit the formation of products. So as we talk about the organization of chemistry, we want you to, at this point in your study, understand how it's going to evolve. And just to summarize that, it's fundamental particles, and those go to elements and atoms, compounds, molecules, then chemical reactions. I should double arrow those. Chemical reactions, states of matter, solutions, and study of reactions. So that kind of gives you an overview of what we're about to do. In this course, we of course will go through the chapter on solutions, but the study of reactions is reserved for Chem 2 and is divided into the kinetics, equilibrium, and thermodynamics. So what I'm trying to do is give you a thumbnail sketch of where we are and where we are going and the study of matter. Now, in the study of science, there is always the scientific method. I would venture to guess that every one of you visit the scientific method at the front end of whatever science course you've taken in the past. And this one is no different than those. We need to visit the scientific method. However, I'm going to present it in a way that has a little different flavor that you may have not dealt with in the distant past. Now, first I'll give you the standard operating issue of the scientific method, and then I'm going to break it off into what we call system and surrounding considerations. And that you may not have been exposed to in terms of scientific study in the past. So here we go. The traditional scientific method, of course, begins with identifying the subject of interest or the problem. Which is the same as subject or object of interest. So you've got to pick a problem and begin to study it. Well, the next step traditionally is collect information or material that deals with that subject. Collecting information on this subject of interest. I mean, this is something you would logically do anyway. Now, in the course of the study, you reading along about the subject, you come up with an hypothesis, an educated guess on how to solve the problem. So, step 3 is formulate an hypothesis, or the hypothesis. On how to solve problem, i.e., that is, educated it's an educated guess. It's exclusively theoretical in its foundation, but you have an approach to solving the problem with generation of some expectations. Now that may be foreign to you. Because you can formulate in your mind, well, if I do this, I should get that. And that's in essence what the hypothesis embodies, an educated guess of how to solve the problem. And if that, because you would have to have an idea of what's coming out of the method that you're about to use. And once this is generated, the hypothesis is generated, then you want to construct and conduct experiments that prove your hypothesis, or just simply prove hypothesis by experiment. So you design and build an experimental protocol, and then you test your hypothesis, your educated guess on the problem. Now, out of the experiment comes conclusions. And a conclusion can be in two forms. Yes, hypothesis is correct and solves problem. Or, let me do it this way. Or, no, hypothesis is incorrect or based on incorrect assumptions. So what do you do if it's incorrect? Well, the idea is to go back and read on the collect information again. So you go back and review what you studied and modify your approach to hypothesis to solving the problem. Well, here's the analogy to that is if you're working math problems. I know as I came through school, I'd work a problem, and what would I do? I'd go back and look at the back of the book, the answer book, and see if it's correct, okay? And so if it's not correct, you go back and you read the book and you work on it, and you modify until you get it correct. So that's kind of a simplified idea of doing it ain't working, so I'll go do something else. So it's like that. So that's the cycle in it. Now, if it is a yes in the context of this, so hypothesis proves correct. We generate two things, a theory or a law. Theories are postulates. Postulates that define the facts that you have observed and fit the facts that you have generated in your experiment. Cooperative word in here is postulates. So you will hear me use that term many times through the course as we talk about postulates of the atomic theory, postulates of the gas laws, postulates of this or that and other. So they're all theories. Now, what the other issue is the law. This is an irrefutable conclusion that is unchangeable. Just, gravity, theory of gravity. If I turn an object loose from my hand, my marker pen, it will fall to the floor. I think we all would agree to that. And it's a simple analogy. But the difference between the theory and the law is the theory is variable. You can add to the theory postulates, or you could subtract from them or modify them. But a law of something is the law of thermodynamics. There are three, well, actually four. Four of the laws of thermodynamics. You can't irrefute them. That we'll get to them. Or the law of gravity, or the law of force and action and reaction. So this is the difference between law and theories. But anyway, that is in essence the traditional and standard scientific method, and I'm sure most of you have already been exposed to that in other science courses you've taken. However, the philosophical foundation for this, and how do you fit into the scientific process, the scientific method, in terms of describing the scientific method in terms of system and surroundings. Now that may or may not have, if anybody have heard of system and surroundings as it applies to the scientific method? Usually none, okay? The essence of my presentation on this is to emphasize how you, as a scientist, fit into the scientific process. This is a T-table. Just go across and down like this. On the left side, we're going to put system. And on the right side, surroundings. By definition, this is real simple, the system is the object of interest. And the surroundings, simply put, is everything else. So in the scientific process, this essentially is the problem. Whatever you want to study, this is the focal point of study. The problem. Okay. It is separate from everything else. And in terms of everything else, it includes you, the observer. That's you. Now, if we're going to study the wall paint or the colors and stuff like this, that wall has to send you signals. It must say something to you. And the essence of the scientific process is you receiving those as an observer, those signals, and interpreting them in terms of what you're looking at. And that implies you are a detector of whatever the object of interest is saying to you. So you, the observer, are a detector, a detective, or scientific detective, or detector in this process. Now, from the side of the problem, you have to observe whatever's going on relative to the object of interest. And how do you do that? You, as a detector, first, this is the most fundamental scientific equipment on the planet in history of humanity or existence, is your five senses. That's the first one. Eyes, ears, nose, throat, taste, feel, whatever they are. What can you surmise about what you're looking at? If we're studying the wall, make a list of what you see. You hear anything? You see anything? If you go up and touch it, do you feel anything? And so you begin to make a list of those items that you perceive about that wall or object of interest. As a result, and at some point, you take that list and you say, the wall is, and you make a conclusion. Now, in the case, I'd say blue, flat, okay? If I put my hand on it, slightly cool. And you draw your conclusion. Is that a fixed conclusion? No, because the wall next door may be different color. So, but you have generated a theory of what that object of interest is and does. Well, that's the same thing that you would apply in science. You are going to study a compound. Well, that compound has to say something to you. It has to send signals to you. And you are the receiver. And the essence of the scientific method is that you as a detector, a detective, receive signals from the object of interest and draw conclusions about what you're looking at. It's not a matter of just running calculations and making lists and filling up pages with whatever. It's a matter of you logically interpreting what you're taking in as a receiver. Now, after the five senses, there are things we do not sense. We visually can see in a very narrow band of wavelengths called the color spectrum. As you know, Roy G. Biv. If you don't know that, R-O-Y-G-B-I-V, that's the colors of the rainbow, Roy G. Biv. If you've never heard of that, red, orange, yellow, blue, green, indigo, blue, and violet, and so forth. But what about infrared? You can't see infrared. How about ultraviolet? You can't see ultraviolet. You do not have the facilities to do that. So what do? Well, here we have IR and UV light, which is the object of interest. Okay, how do you detect it? Well, you have instruments. And these generate data, and that gives you your conclusions. The majority of the scientific effort is in the construction of devices that can detect information sent by the object of interest. Stars. How do we study stars? Based on whatever the star sends us, and that's all just 99% light. And from whatever that light is, we draw conclusions about the nature and behavior and character of stars and planets. What does the object of interest see? Same way with the chemical reaction. What kind of changes would you observe and mark down and then interpret in terms of whatever the object of interest is? Those are referred to as physical and chemical properties. So we categorize a process or reactions have chemical and physical behavior that we call properties. Brittle, hard, pliable, ductile, liquid, whatever. Okay? Or things you can't see. How does this compound interact with this compound? It might give off heat. How are you going to measure that? Thermometer, maybe? It's all the instrumentation. And heat comes from whatever that reaction does. And you note it on this instrument called a thermometer or thermocouple. And you say, okay, the temperature went up. What does that mean? Or the temperature went down. What does that mean? So you draw a conclusion. People call them endo and exothermic reactions as they apply to the system. So let's say we run a reaction over here. And you have a thermometer over here. The thermometer, the solution it's in, the water, all of it, everything else is the surroundings. The thermometer is part of the surroundings. And you observe, as a result, increasing temperature. What does that mean in terms of the reaction? That means the reaction lost energy, because the energy that the reaction lost was sent into the thermometer and it absorbed by the thermometer. The surroundings is always doing what opposite of whatever the system is doing. And so in increasing temperature, this is your interpretation is system lost energy, and therefore we call it an exothermic reaction, because you detected something over on your side of the petition here. It's what you interpret, because you are essentially part of the surroundings. Now, if you approach this course like this, then you would have a more sensitive idea, an appreciation for what's going on as we go to lab. We pour A and B together, how are you going to measure their interaction? Well, it might be a thermometer, it might be a pH meter. pH goes up or goes down, and that says something to you. It's the language that is delivered to you and how you interpret that language. That's a chemistry course. They give you a problem. It's got all this gobbledygook data in there. That's signals being sent to you. It's a language. And this can be summarized, and I'll get off of this now. Einstein said, if you want to know the secrets of the universe, understands what he's saying. You must first learn its language. So this entire course is teaching you a new language. For some of you, you will proceed through it very smoothly and effortlessly. Some of you will not. I'm not very good at this, that, and other. Well, if you approach it from the standpoint of, well, do I have the tools as a detector to make a reasonable interpretation of what signals are coming out of this problem, the data. You learn to take the data, manipulate it through mathematical principles that I'm going to show you, and you ultimately draw a conclusion that applies to the system that you have an interest in studying. Now, that's a generic cross-section of the scientific method you may not have ever heard before. I dare say anybody said it. But it makes sense in terms of how you approach the scientific process. If you realize who you are in that process, then you will be a more effective scientist in applying your skills and developing your skills and applying those skills to a positive, constructive endpoint.